So we've made our pipeline. We have looked at the different ways that it can go wrong with pipeline stalls. We've looked at fixing the structural hazards, which for small pipelines we don't typically have. We looked at fixing the data hazards. We looked at data forwarding for that. And then we did some analysis of performance. But now we get into the meat of branch prediction, which is the way that we try to improve the performance of branch hazards. Whenever we're making a decision and we don't know if we're going to instruction code or instruction chain A or instruction chain B, we have the options of either just waiting or trying one and hoping it's the right one. In the real world, this is always going to be faster to try one instruction chain and hoping it's the right one, because the penalty for losing this, the penalty for misprediction is flushing the pipeline and starting again, which will be more than if we inserted bubbles. But if we get it right even half of the time, and branches are 50-50, I mean, they're not 50-50, but it's one thing or another thing, right? And if we get it right half the time, then we're going to make up for the fact that the cost of flushing a pipeline after a mispredicted branch is more than the cost of just inserting bubbles anyway. But that means the better we can get at predicting branches, the better we can get at our performance. So how do we predict branches? There's a couple of ways to do that. We can look at repetition. We can say, we've been through this branch before. We've seen this in context before. I know that every time I look at this branch in the code before, I took the branch. So I'm going to guess that I'm going to take it again, right? This is code repetition. The other way to look at is code parallelism. If I see branches in this context, or if I see branches nearby, I see in the past that I have not taken those branches, so I'll try to not take that branch again, right? In a switch case, for example, there's a whole bunch of branches, and it's only going to do one. So it's a pretty good bet to predict that you're not going to take any branch in a switch case. You're going to be right most of the time. You're only going to be wrong once, and that wrong means you flush the pipeline. So that's parallelism in terms of trying to predict the branches. So what do we predict? We can start by making some naive assumptions. We can always predict no, and just load the next instruction after the branch, right? Because if we branch yes, right? If we take the branch, we go somewhere else. If we don't take the branch, then we just execute the next instruction after that branch instruction. So we could just do that. We could always just start predicting the next instruction, and that's going to do okay, because a lot of the time we don't take a branch, and then we just carry on with what we're doing, right? It's the stopped clock is right twice a day kind of a thing. In fact, there's another branch prediction thing that I don't think is in these notes, which is random. Just roll a dice and guess. And that's right often enough that it's going to be useful, and then we don't incur the expense of complicated, difficult branch prediction schemes. However, complicated, difficult branch prediction schemes are good enough and correct enough that we actually do them in the real world, and so we're going to look at how those work, right? So first option, just always predict not taken. Second option is looking at program context. If we don't want to do loop unrolling, because we don't want to fill our instruction cache with multiple copies of the same code, then we can check context and say, if we're doing a loop, then we're going to predict branch every time, because most of the time when we do a loop, we are going to branch back to the beginning again. So we can do a predict always taken with a loop, and that'll be right most of the time. The only time it's not right is when we don't take the loop, when we don't take the branch, and we do that at the end of the loop, right? We can also use compiler and programmer clues. There are ways for the assembler to write code to make a suggestion to the pipeline to say, I think it's likely this branch is not going to be taken, right? I'm checking for a really weird edge case here, so probably it's not going to be taken. So I would encourage you to predict not taken, right? You can actually put that into your code and give a hint to the pipeline as to what is the likely outcome, right? So failing those things, though, what do? Well, the machine can keep a history of when a branch was encountered before, and then use that to decide how to predict the next branch. We call this dynamic branch prediction. We need all sorts of extra hardware for this that happens down at the low level. We're going to add a little bit of a cache, another little chunk of memory, right? Just like the translation look-aside buffer for virtual memory, or an instruction queue for a prefetching dispatch cache, a little bit of extra memory that's going to hold information about branches. and it's going to have, the address of the branch, and it's going to have what happened the last time. And then we need a bit of hardware to say, if it was taken last time, should we take it this time? Because it's not always clear whether we should always do what we did before or whether we should sometimes do what we did before. So the way we're going to do this in the examples in this video are with a 2-bit branch prediction finite state machine. We know how to build finite state machines. Why shouldn't we throw in a finite state machine for any number of branches that we encounter? What could go wrong? Here's what it looks like. Oh, and I'm in the way again. It's going to be, let me just actually fix that really quickly. How's that? Is that better? I'm not in the way anymore. See, we'll do it. We'll do it live. We'll make it run. So dynamic branch prediction is the idea of keeping a history of the branches that we have encountered in the past and then using what we do each time to make a better prediction of that same branch in the future. So this is an individual branch and an individual line of code, and then we make a decision based on that. Now, typically these finite state machines are implemented like this, where we have 2 bits of history, and we say the last 2 times we saw this, and so we're going to do this, do a different thing. This example is what we call a saturating predictor, and what this does is, imagine, for example, that we see a branch and we take the branch. So we're going to start here, for example. We call this weakly taken because it means that if we start to not take the branch, it's actually easier to get out of that history. But let's look at the whole history. So weakly taken here. And then if we take it again, then it's strongly taken. And we predict it's taken over and over and over again, right? If we continue to take the branch every time we see it, this will work fine. If we don't take the branch once, like at the end of a loop or something like that, right? We still predict it's going to be taken the next time. Because a single incorrect prediction, we don't want that to undo the history that we've developed over time. This kind of a saturating branch predictor is useful in contexts where you might have a loop that goes around and around and around, but then after that loop is done, or if some other condition is taken, we never enter the loop again, and every time we see that branch, we don't take it, right? So if in one context, when we operate under this code, we take the loop over and over and over again, and then once in a while we don't take it, but later on we find ourselves not taking the loop over and over and over again, and once in a while we take it. So we have to be wrong twice in order to start predicting the other direction, right? If we're predicting taken, we have to be wrong twice before we start predicting not taken. And that works pretty well. The other sort of typical way of doing this is what we call a hysteresis predictor. And this says we can predict most of the time correctly, but if we predict incorrectly, we assume that things have changed, and we're going to immediately jump to predicting in the other direction. So we predict strongly taken right here, right? If we don't take the, we have to get it wrong twice, right? We predict not taken. We don't take the branch. We still predict taken, but weakly. Then if we're wrong again, the hysteresis predictor will say, you know what, we've been wrong twice. I bet you we're now in the non-taken zone. So we skip right to strongly not taken, and then we have to take it twice before we can predict taken again. Okay? So what this does, it solves a small problem, with the regular saturating predictor, is that you can get this weird situation where you are going back and forth predicting that you're going to take it, but then you don't take it. And then you predict you're not going to take it, but then you do take it. And you can just get infinite wrong predictions, okay? The hysteresis predictor will fix that problem. If you predict weakly taken and you don't take the branch, then you jump right into strongly taken. And then if you're going yes, no, you're still going to predict correct half of the time instead of none of the time. So these kind of complexities of what actual algorithm you use to predict the branches gets really messy, and this then becomes more of a software theoretical thing that gets implemented in the microcode of the finite state machine or the branch prediction cache that implements these kind of predictors. And it really is a little micro cache, just like this, right? You're going to store the program counter value for each branch that you encounter and choose to predict. And this is going to give you quick access to the predicted value that you should decide what to do. And again, you can add this to any pipeline, and the pipeline doesn't have to know about it. All you have to do is say, I'm encountering a branch at this address. What does the predictor say I should do? And then it'll say, take this branch. And then the pipeline will be, all right, I'll take this branch. I'll start executing these instructions instead of those instructions and just carry on, all right? So this kind of a thing, we call this a branch target buffer, a little tiny micro cache that will allow you to decide what to do. Other implementations will go one step further and say, I'm going to predict this branch, but also I'm going to load the next instruction, or at least the next opcode, for what happens if I get it wrong, right? So this is sort of the road not taken. I'm going to actually just sort of begin the process of maybe hinting at loading the next instruction on the branch I predict to not take, right? So if I'm going this direction, I also want to look over my shoulder going this direction. And so we're going to load the opcode at the same time as loading the predicted program counter, and that allows us to make the flushing a little faster. If we get it wrong, we have to go back in time and flush the pipeline and start again. This allows us to sort of jumpstart reloading the pipeline if we get our prediction wrong. So it's another neat kind of trick. One last thing about branch prediction, two-level branch prediction, where we're not just predicting the branch, but we're actually predicting based on the last two times we saw this branch. This allows us to build prediction schemes for complicated sequences, right? Maybe this branch that we see, we're going to take it twice, but then we're going to not take it. Any of those single-stage pipeline or any of those single-stage branch predictors aren't going to work well on this. But if we implement a two-level branch prediction, where we take a look at what happened the last two times we saw this branch, then we can do some really neat stuff. It's a much more complicated system. Because we need a complicated finite state machine for each branch. Instead of just a simple finite state machine, we need a complicated finite state machine for each possible sequence of branches at each program counter. Not just each branch, but each sequence of branches. So I'm in program counter A. The last two times I saw this branch, I took it and then I took it. Should I take it again? That's what this does, right? Again, then program counter A, the last two times I saw it was taken and not taken. That's a different prediction, right? So here's an example. If I see a sequence of sort of alternating branches at a particular program counter, not taken, taken, not taken, taken, not taken, taken. Maybe I'm looking at a 3-bit history, a 3-event history. If the last 3 times I saw this branch were not taken, taken, not taken, I'll predict taken. But if the last 3 times I saw it were taken, not taken, taken, I'll predict not taken. And so I can encode complicated sequences of branches if this is going to be useful. This gets really, really messy, really complicated. Lots of hardware required, because now you need a finite state machine for each possible sequence of branches at each program counter. But we can much more accurately predict branches. This is good for longer, more complicated pipelines. But if we simplify our pipeline, the branch hazard consequence is less, and so we don't have to spend as much time implementing these things. Because not only do we have to have a finite state machine for each sequence of branches, but we have to think about whether we're predicting locally or globally or per branch or set history or adaptive or static or global. It gets super, super messy. There's a lot of cool stuff. For any kind of thing we're adding to a pipeline, we can imagine almost any level of complexity to add features to allow things to work properly. But in the end, we're just trying to predict the future, and maybe the easier thing to do is just not look so far into the future, right? Keep a smaller pipeline that we don't need any of this stuff for.